Okay, so there are basically three principal sources of optimization. Among them are local optimization within a basic block, global optimization is otherwise, and mixed. Let us discuss function preserving transformation. Function preserving transformation is to improve the performance without changing the function. The common techniques used for function preserving transformation are common subexpression elimination, copy propagation, dead code elimination, and constant folding. Okay, so now coming on to common subexpression elimination. An occurrence of an expression E is common subexpression if E was previously computed and the values of variables in E have not changed since. Copy propagation. An idea behind this technique is to use G for F whenever possible after the copy of F is equal to G. You can see an example of the code in the slide. Okay, so now coming to the dead code elimination. Basically, dead code elimination means that you remove unreachable code. By unreachable code, I mean which cannot be accessed from the initial state. Okay, so now coming back to loop optimizations, there are three important techniques: code motion, induction variable elimination, and reduction in strength. Code motion. Move code outside the loop since there are potentially many iterations. Look for expressions that yield the same result independent of the iterations. You can see an example of that in the slide. Okay, so let's discuss now induction variable elimination and reduction in strength. So we have to look for induction variables for strength reductions. Taking an example, a pattern of changes in a lock step, and an example of this can be seen in the slide. There are other optimizations such as optimizations for basic blocks, reducible flow graph, global data flow analysis, machine independent optimizations, but we will not be discussing those topics in this video. Okay, so in order to draw a transition diagram, we have to look at the first symbol of all the inputs, and then for each distinct first symbol we will need intermediate state from the start state, and then for each symbol after the first input symbol we create another state. If this has fulfilled all the inputs, then we have the final states. If not, then we follow the same procedure by making these new states as intermediate states, and if necessary continuing from them to the final state, and this goes on for as long as the input goes. This is the transition diagram. In this particular case, plus and minus are the starting symbols for two inputs. So because of that, the intermediate states 1 and 2 have two final states each, whereas is equal to and not operators have only one final state each because they are only the starting symbol and only two of the inputs of the input each.